Welcome again to my GIS lab. Here I will show you a few practical applications when you use the raster calculator. We will discuss the creation of integer rasters from floating point rasters, simple queries, and the implementation of equations in spatial models. One thing we regularly need to do is we need to take the integer of a raster file, because raster files have lots of decimals. Many are by default floating point rasters. And for certain analyses, we need to convert our raster files into integer files. The integer command works the same in ArcGIS as in many other programs such as Excel. I have here a few numbers that I want to take the integer from, and I do that by using the integer command. For example, integer of B3 is 1.27, so the integer of 1.27 is 1. Well, we accept that. But is the integer of 1.99 really 1? Should it be 1? And we can see instantly what happens doing the integer command. What the integer command does, it simply gets rid of the decimals. It deletes the decimals irrespective of how high the decimals are. If it's small or if it's high, it just truncates them. So 1.99 becomes a 1 and the 2.01 becomes a 2. In most cases, this is not what we want. So our integer command would fail us and would add an error in our conversion from floating point to integer, an error that is larger than what we want. There's an easy fix to this. All we need to do is we go to our number and add half. And if we apply this for all other ones, now we have a logic that works. 1.27 becomes a 1, so basically now we're rounding. 1.5 plus half is 2, integer becomes 2. 1.99, this is now becoming 2.49, and we truncate the 49, becomes a 2. We can see now that the range from 1.5 to 2.49, all these numbers become integer numbers of 2. And we can apply exactly the same logic in our raster calculator. All we need to do is add half to our input values. And we carry this out in the raster calculator under Map Algebra. I want to take the integer, so let's find the integer command in here. There's our integer command. These are Python script commands also, and they are case sensitive. So int must have a capital I, small n, small t. Any other spelling would not be understood by the raster calculator. So not once the input file, which is our DM, and all we need to do is add half to the entire DM. And we would give it an output file name, but the key thing here is your syntax, how you take the proper rounded integer of a number converting from floating point to an integer raster. I used here on purpose a different color scheme. The values inside are not quite different. You see here the max is now just 166, so the decimals have been simply deleted. And as we have just discussed, the correct form would be if we add half to our raster file and then take the integer, and this would have been then the correct grid. And you see here now our maximum value is the correct value. Let's give ourselves a simple task. I'm looking for all areas that are greater or equal 1300 meters elevation and that have a gradient of greater or equal 15%. We do that in our raster calculator. We define our output raster name. In my case, I want to call it FH for foothills, and then elevation over or equal 1300. And the query itself is extremely simple. My elevation model in this case, greater equal 1300. That's all I have to say. So remember, when you type this in by hand, that your existing layers are in quotation marks. And if you're not sure about the syntax here, you can find your math equations here as well. So if you say over equal or under equal, the equal sign always comes last. And I've already executed this, and here's my resulting raster layer. Everything that fulfills this query, everything that is true following this query, is assigned a 1, and everything that is not true is assigned a 0. And it's easy to make the symbology more useful, and I've already done this over here, where I make my 0 transparent and I give it a full color to anything that fulfills my condition. And then also, it may be a good idea to make this transparent or half transparent. Let me show you the raster calculator syntax for all the other resulting rasters. And I do that by going back to my history. And here was my first query. Here is my second query, where I say slope percent is greater than or equal 15% in this case, but of course we do not use units in our raster calculator. And then we can combine the two output rasters by simply adding the ampersand sign, or we can also say AND for and that simply then says if everything here is 1 and everything here is 1, then it's considered true, and if it's 0, it's considered false. And the result of that looks like this. Where, let me show you first, this is my resulting slope query. Everything over 15% is coded as 1. And here is my resulting overall query. So now the bluish areas are both slope over 15% and elevation over 1300 meters, over equal 1300 meters. We can make our life easier by combining both queries into one longer equation by simply saying elevation over equal 1300 and slope over equal 15. However, as you can see here, when I filled out this, I received an error message, and here is a warning sign that my raster calculator did not execute properly and did not create an output file, because our syntax here is not right. If we combine two individual queries like this, all we need to do is we need to add brackets around our left and right terms in this case, and then it will execute, and the result here in purple is exactly the same as the result that we had earlier, where we divided it up into 3 individual steps. In order to create a raster surface with calculated temperature values based on an elevation model using the lapse rate is relatively straightforward. But what we need to know to calculate the temperatures, we need to have a reference temperature. In our case, we assume that a climate station is 1,000 meters elevation with an assumed April temperature of 3 degrees. And of course, as we go up in elevation, the temperatures is declining. The lapse rate here is -6 degrees per kilometer, but because our elevations are in meters, we want to keep the units straight, so we simply divide 6 by 1,000, and so it's minus 0.006 degrees per meter. So the logic is simple. We use the temperature in April, and now here's our minus, so that minus sign comes from our negative lapse rate. And all we have to do is, for all the elevations that are in our elevation model, we have to relate them to our climate station. So we simply subtract 1,000 meters from our elevation values and then multiply by our lapse rate. So this part here is simply the difference between our climate station and wherever you are within your elevation model. Temperatures will be lower than 3 degrees as you go up in elevation, and warmer than 3 degrees if you go lower in elevation. We can apply our temperature model in our raster calculator, and I've already done this. And here is my equation that we have just developed. And here is the result. So here I have now air temperatures between roughly +3 degrees and -3.3 degrees. I applied a nice color ramp that I liked, and it's probably a good idea to put our hillshade on top here. And now we see that the higher elevations are colder and the lower elevations are warmer, exactly what we expect. Now that we have our temperature model, we can do a simple query. We can find out which areas have a temperature in April over 0 degrees, assuming that it snows when it's below 0 and rains when it's above 0. We take our temperature service that we just created and say, give me all the areas that are under equal 0. And again, here is our result. And all these areas here would snow according to this model. But in reality, the threshold value between snow and rain is not really 0 degrees, it's actually +2.2 degrees. So we can run this again, of course, in our raster calculator, just doing another quick query here. And the result looks something like this. We're here now in the bluer area. We have now, when it already snows at +2.2 degrees, we of course get a much larger area where we have snow. So here we have two different snow models based on our temperature model. And as long as you are confident that your input values were right in terms of the temperatures and the location of the climate station, etc., etc., then you can trust your rough model where we have snowfall predicted for two different conditions. In order to derive the equation that resembles our habitat suitability curve, first of all, we need to derive our slope. And our slope, of course, is rise over run. Rise is 1, run is 10 here. So the slope is 1 divided by 10, or 0.1. And when we look at the derived slope, it does not cross the y-axis at 0. It crosses the y-axis at -1. That's why we have to simply subtract -1 from all locations of the curve, simply by adding -1. And then the last thing is prevent our values to go larger than 1 and smaller than 0. We do that, of course, with two simple con statements. The simple curve that we want to apply here in GIS is our distance to roads. So here, to derive our slope, again, is simple. It is 1 divided by 250. That is our rise over run. And when we extend our slope line, all we need to do is prevent it from going larger than 1, again using the con command. Now let's implement the bare habitat suitability equation for roads that we have just established. We have our road file here. We would use the Euclidean distance tool to calculate our distance raster. Of course, we make sure that the raster is snapped to other existing rasters for proper overlay analysis later on. And here in my distances, you see I have incremented them by 50 meters, and the threshold under 250 meters is all here still the light green. I have also calculated a buffer. We don't need this for the analysis. I just added it for our visualization here. So this is our 250 meter buffer. And then when we go in and apply our raster calculator equation, here you see the equation that we have established. If the road distance is over 250 meters, the habitat is 1, highly suitable. And if it's less than 250, apply a linear equation that up to a distance of 0 would then become 0. The result looks as we expected. Here again with our buffers just overlain. That here our suitability improves gradually with the distance of the roads. Of course, in my case here, my colors are reversed because right now I have for low suitability green and for high suitability red. I want to flip this over. I do this under More and reverse my ordering. Now this map makes way more sense. The suitability index increases with distance from road, 0 at the road, up to 1 at a distance of 250 meters. Mission accomplished. That's all for today. Until next time.